And done. Alright, what's next? Ooh, okay, something with boxes. Alright, hold on. What does it say? Start, press the stop for. Well, that's not helpful. What even is this? Oh, okay. Okay. Hold on. Maybe make what is dim bright. Make what is dark light. Okay. Wow, no! Okay, so what, like... Then it changes the neighboring... Oh, wait, hold on. Okay, so it's all the neighboring blocks, so I can just go whap. Whap. Okay, that wasn't too hard. Hey, this is like that earlier puzzle where I had to turn the boxes, like, okay, so like... How do you... oh, okay. Right. Close, I think. Wait, hold on. Yeah, I can do this. Process of elimination. What? There we go. That was annoying, but at least it's over now. I hate this stupid forest. I hate getting... Oh, I'm lost again. Great, I hate this place. This place sucks. Oh, finally! Great, alright. I'm here. I brought the key. Let's do this, bad boy. Take me to the speakeasy. Alright, oh, and it's another puzzle. Okay. That's... This feels familiar. Why does this feel familiar? Okay, finally. There's no way the gold isn't down this well. Alright, let's go. Let's go. End of the game, baby! I'm the greatest mystery solver. What? Oh, it's another puzzle. Okay, oh, that's fine. I can do another. Uh-oh. They affect each other. Wait, this is familiar. Wait a minute.
Okay, stop. You might have noticed the pattern by now. We have here puzzles of a specific variety. There are letters or numbers or lights that can be switched. Interacting with any of these pieces will change that piece, which is what you instinctively do to input the desired combination. But this will also result in other pieces changing as well. So knowing the right combination is usually not the problem. The problem is actually trying to input that combination. I'm sure you've all seen this type of puzzle before. Have you ever wondered if there's some algorithm by which you could solve them? Well, the puzzle on screen made me think that. I mean, just look at it. So I worked on a mathematical solution instead of messing around in game. But then I realized that I could describe a general method for solving such puzzles. This method uses systems of linear equations. Well, it kinda does. It actually uses a system of linear congruences. This means we'll be using modular arithmetic. I'll be discussing my general model, then I will go over all of the examples shown in the opening montage. I will also showcase applications of the solutions in speedruns. One more thing before the video starts proper, I will leave a link in the description for a Google Drive containing the PDF documents shown in this video, if any of you are interested in that sort of thing.
Okay, so for here I'll mostly just be reading off of the model document I made and interjecting where I feel it needs to happen. So the general model then is that you have n nodes, where n is like 2, 3, 4, so on, and the nodes then are like the individual characters on the tombstone or the individual squares in the Undertale Yellow puzzle, and then each node will have m distinct states, and those will then be like the different brightness levels of the squares in Undertale, or the different numbers in that puzzle at the end of Ghost Dogs on Moon Lake. And yeah, and then for these states, the states of the nodes have a cyclical order, and interacting with a node will cause some number, potentially 0, of nodes to change to the next state in the order. And so that's what we saw like with the numbers, where they'll go 1 up, or if they're at 5, they'll cycle back to 0, I'm not sure if it was visible in the gameplay of the Tomb Puzzle, but they also had a set order when they'd cycle back. And so, yeah, but there must be at least one node that causes at least one other node to change its states, because if none of them change other nodes, that's kind of boring. They either change nothing or they change themselves. That isn't really in the spirit of the puzzle. And we can immediately deduce from these facts that the order of the interactions won't make a difference to the end result. It's kind of like commutativity addition. Because all the same interactions are happening just in different orders, so it's the same result. The puzzle is considered to be solved when a specific configuration of states is possessed by its nodes. So, for example, in that puzzle where it said Waldo on the tombstone, the solution configuration would be Baldo. And importantly, the solution configuration must be distinct from the starting configuration, otherwise there isn't really a puzzle. And any combination interactions that solve the puzzle is considered to be a solution, and repeatedly interacting with a node is allowed under a solution. So it's like with that first puzzle in Undertale Yellow, in like interacting with the second node and then interacting with the third node, I believe, is a solution. So yeah, that's the solution. Is the combination of interactions. And well, for a given, and up next we have some variables that are being defined. It looks like this: for a given solution. So these variables are defined for a solution. For a given solution and an integer j that ranges from 1 to n, we let x of j be the number of interactions with node j. So with that solution I mentioned, where you interacted with node 2 and 3, x of 2 would be 1, x of 3 would be 1, and then x1, x4, and x5 would all be 0. And then y of j will be the number of state changes experienced by node j. So this isn't the amount of times you interact with it, this is the amount of times it's changed by interactions, so potentially from other nodes interacting with it. So with that Undertale Yellow puzzle, that would be y1 is 1, y2 is 2, y3 is 2, y4 is 1, and y5 is 0. And then zj will just be yj mod m, so mod the number of states. And so if you have like 5 states and y3 equals 7, then zj will be 2, because that's 7 is 2 more than a multiple of 5. And I want to remind you at this point that you can't kind of just wind through this section and skim read this stuff. I'm only basically reading it to elaborate where I feel something might be confusing. So yeah, you can just skim through it if this is too slow for you. But yeah, next we have that it immediately follows that xj, yg, and zj are all whole numbers, because you're not going to interact with any of the pieces a negative number of times. And also cj is, defined as yj mod m. So it's not gonna it's because yj is already a whole number, it's not going to be made smaller by the mod operation, so zj is going to be smaller than or equal to yj. Also, we I denote solutions by the number of times each node is interacted with, so by the ordered n tuple of xj for all of the j that we mentioned in the range from 1 to n. Yeah, that's what this down here for all xj means. So we've got the x1, x2, x3 up to xn, and the n tuple of all of those numbers is how we denote the solutions in the document. Oh, mosquitoes. And we also have these values a, j of k, which are basically coefficients to our linear congruences. And how they work is that for a given solution and the integers j ranging from 1 to n and k ranging from 1 to n, a of j comma k is equal to 0 if the state of node j isn't changed by interacting with node k, and 1 if the state of j is changed by interacting with node k. So basically it's like a Boolean value. Does interacting with k affect j or not? Okay, sorry that I just advised that you can like skim read if you want to, and now there's suddenly an edit in the document. I saw a mistake, but I mean, at that point, if you want to skim read, you can just download the PDF in the description, because that's going to be the final version. So without the mistakes, but yeah, so moving on. With that Boolean value for the a of j of k, we can then get a formula for y of j very easily. Because you see, if interacting with node k doesn't affect node j, then it has no impact on how interacting with node k then has no impact on how many times the state of yj has changed. So the value yj, on how many times the node j has changed, and the value yj is how many times has that state changed from all nodes that interact with it, right? And so it's gonna just be equal to the sum of all of the number of interactions with nodes that affect it. Hence, a of j of k is useful here then, because it'll equal 0 when the node interacting with the node doesn't affect it, hence eliminating that term from the sum and just 1 to keep the ones that do affect it. So it forms a nice trivial series for y of j, which is a useful formula. Another thing we have to find is the complexity of a solution. We denote it by capital X. It is defined as the sum of all of the x k's, all of the number of interactions with each individual node, So it's just how complicated is the solution, how many times did you have to interact with nodes. And some final terminology. We consider a solution to be simple if for every integer from 1 to n, we have that x of j is less than n. So basically that you interact with it for a smaller number of times than the number of states, which will become clear under the theorems why that definition is chosen. And a solution is considered to be minimal if there exists no solution for the given puzzle with a smaller value of x. So keep the same puzzle, the same starting and ending configuration, and the same interactions between the nodes with each other. And other solutions with that exact same puzzle, the same things. If any of those other solutions are less complicated, then your solution is not minimal. It's only when none of them are less complicated it'll be a minimal solution. And then this, of course, means you can have multiple minimal solutions for a given puzzle. They all have the same lowest complexity, but yeah, and we're of course interested in this concept because why have a solution be more complicated than it has to be? That's kind of a waste. And we explore that concept in the math I've worked out here. We explore it. Alright, now for the theorems. I'll be less hands-on in explaining it here in audio now. I'll just mostly scroll through it and you can read the theorems and the proofs. I'll explain a few things about it. So for here we have, I'm saying that the z of j here is a constant with respect to the solution. And so what that means is, for your specific value of j, it will not, and for a specific puzzle, so these two are now set in stone, you can choose whatever solution you want in that context, and the value of zj will not change within that space, is what that means. And we have, yeah, so here you have your normal solution x1, x2, all the way to like xn, and we're saying that u1, u2, all the way to nn will also be then a solution for under the rest of the conditions stated here. I said I won't be reading as much. Okay, so here's a confusing one as theorem 3. So what's happening here is, in the proof, is that u is a substitute for our x's. It's like one of the x's, which is not conforming with, so we have here, of course, that the x1 mod m, x2 mod 2, so on. It's going to be the only minimal solution. So this is like a supposed counterexample, one that the minimal solution that isn't that exact configuration. So this u is a substitute for one of those x mod m's, and the v would be the index for that x. And what we'd have then is u has to be congruent to xv mod m, because it said so in the conditions for theorem 3, is a constant with respect to the solution, xj mod m. And so it will remain congruent. However, it's supposed to be, in order to be a counterexample, it can't be the same as that xv mod m as in the solution. And so, but in order for that to happen, not be congruent to xv mod m, or not be equal to it, but to be congruent to it, and then also to be in the range from 0 to m, excluding m, it can't be all three of those at once. One of those has to give away, because within any range between multiples of m, there is only going to be like the one number congruent to mod xv mod m. And so that one number is, of course, the number we said it's not equal to. So it's a contradiction. That's what the proof is saying. Right, now on to the actual method which these theorems are used for. So what you want to do is you want to construct a system of linear congruences of form zj congruent to yj, which is then equal to our formula, which is why a formula was needed, all mod m. And you will make like a formula of this whole form for every possible value of j from 1 to n. So that's your n formulas or your n equations or congruences in your system. And then by theorem 1, which you'll recall is that for any solvable puzzle, the zj is going to be constant with respect to the solution. Because of that, the zj in our system in each single formula can be known. Is we can look at the puzzle and we can determine it. It's basically the minimal number of times that you want that specific node j. It's the minimum number of times it has to switch before it's on the solution state for the first time. And so if it's already in the solution state, it'll be 0, and then otherwise, it's going to be some number larger than or equal to 1 and less than m. And so that can be known, which gives us something to make the sum on the right congruent to a constant, a number, And yeah, from there, for the most part, you can treat it as a normal system of equations when solving for xk, but with the caveat that you're not saying, when you do an algebraic manipulation, you're not saying that the new equation is equal, you're saying that the two sides are congruent instead of being equal. And there's also another rule, or two more things. There's the important disclaimer, you can't divide. So if you have like 3x equals 2y, or no, sorry, in this case it'll be 3x congruent to 2y, you can't then say y congruent to 1.5x, right? with congruencies, division doesn't always work. I have here an example. 4 is congruent to 1 mod 3, but 4 divided by 2 is not congruent to 1 divided by 2 mod 3. And that's because 4 divided by 2, that's 2, which is then congruent to 2 mod 3. It's not congruent to a half mod 3. So you can't divide, but we do have alternative, is because of modular arithmetic working in cycles. You can just subtract multiples of the mod, right? So like with the mod 3 example, you can subtract or add multiples of 3. And since the variables are all integers, you can increase or decrease their coefficients by like multiples of the mod. And so I have an example, as you can add, here the example, the congruency -4 is congruent to 4x plus 4y, where x and y are integers, can be simplified to -1, which is adding 3 to the -4, congruent to 2x plus y, so those coefficients 5 and 4 are each reduced by 3. So this can often allow you to get a coefficient of a variable down to 1, and then allow you to say then that the variable itself directly is congruent to this or that, which can help you circumvent division. Also then, the quirk of the system is your final solutions isn't that xj is equal to this or that, like x2 isn't, you won't say x2 equals 5, you'll say x2 is congruent to 5. And then what this means is that any possible whole number value for a variable that is congruent to the number you said it's congruent to will work. So for example, if you say that x3 is congruent to 1 mod 5, then that means x3 can be 1, it can be 6, it can be 11, it can be 16, so on. But we, like I mentioned before, we're interested in the minimal solutions. So what I've done is once I have these congruencies, I just set them equal to the smallest number, that smallest whole number, that is congruent to what it's ever congruent to, whatever it is congruent to, which just means setting it equal to xk mod m, as an operator. And that will result in a minimal solution. It will result in a simple solution, which is why we were interested in having the simple solution be defined by m, was because xk mod m is always going to be less than m. And so there will always be a simple solution. I mean, that was one of the corollaries in one of the theorems earlier, was that there will always be a simple solution. And that a minimal solution is always simple. And now, when you've solved the system and given a congruent value to each of the variables, usually the condition for theorem 3 will be met, which means that the solution you end up with will then also be a minimal solution, and usually the only minimal solution.
Okay, so now what we're gonna do is I'll show a video of me interacting with the puzzles, where I basically show the length of the cycles and I show what characters or like what states are in each node cycle, and then I'll show the math in a document where I go over it. So basically the footage to just show where we derive the variables from and the systems of equations that we're using, or the systems of congruencies and the formula. So that's going to be the format, is video of interactions with puzzle, solution, and then I'm going to show speedrun where the solution is implemented. So it's going to be like the world record speedrun for these games. So it's going to be, the format is interactions with puzzle, math, speedrun. That's going to be the next segment.
So we saw the node 1 only needs to be changed once because it's dark and needs to be made bright. And then node 2 and 3 are both already light, so the minimum number of changes is 0. That's going to be the C2 and Z3. And then it's going to be 1 for node 4 and then 0 for node 5. And we saw that node 1 is affected by nodes 1 and 2. So we've got x1 and plus x2. And now node 2 is x1, x2, x3. Those ones affected. And then 2, 3, 4, 3, 4, 5, more 5. You can see the patented footage. This is just how all of the formulas are going to be derived. And from there, I'll just scroll through at a reasonable pace. It's just going to be then, like I said, mostly just normal solving of a linear system with out division and with some modular operations added to the kit. Oh yeah, here we have, sometimes it happens that the system is such that there isn't one exact solution. And then what we'll do is, since we want the minimal solution, this wasn't detailed in the model document, but we'll try testing different possibilities to see what produces the minimal solution. So here, for example, we see everything is congruent to x1 by, or has a formula in terms of x1 for its congruency. And we can't solve further for x1. So what we do is we consider the possibility that x1 is congruent to 0 and that's congruent to 1, and then we insert it into the formulas for 2, 3, and 4 here, and that way then we check what the complexity is of these different solutions. And we see that x1 is congruent to 0 produces a complexity of x equals 2, and the other one gives big X equals 4. So our capital X is minimal when x1 is congruent to 0. So that's what we're gonna go with, x1 congruent to 0, so that we may have our minimal solution. And then you just substitute back in, and then we have 01100, which we will now show. I will now show the footage of in practice. Okay, same deal. Node 1 gets interacted with 0 times, and I had, the minimal number of attempts before it reaches the correct state for the first time is 0. It's interacted with by nodes 1 to 6, and you get the pattern. You know it by now. So we just have the formula generating, and we start solving it. Nothing too special. And we have again, we end up with the situation where there isn't an exact final single solution, and we have to consider cases. And in this case, because of how many variables there were, we didn't already have all of the variables in terms of x1, because we kind of skipped doing that just to substitute in for the next, to find the next variables formula. So we just go back and do the substitutions needed to find the formula in terms of x1 for each and every variable, and substitute that, and then do cases, and we found the case that works is x1 equal to 0, or congruent to 0, yeah, and it ends up being the same because we're just going to set it equal to it, like I've said before, so it doesn't really matter if we say congruent or equal in this circumstance. But yeah, it ends up x1 produces the smaller capital X value. I mean, x1 equals 0 produces a smaller value, so that's what we go with. And we have a final solution where node 4, node 7, and node 8 are all interacted with once, and none of the others are interacted with. And that's now cue the speedrun footage. Now, in this case, we do get lucky. I'm not even gonna bother. You know the pattern by now. You can look at the system of congruences. But moving on past that, we get lucky in that there is only a singular solution to the system. We didn't have to make our own specifications to narrow down the solutions to the minimal one. It just spat out what we wanted, which sometimes you get lucky and that happens. Now here it happens again that we get lucky. It does end up with one solution precisely. So here we go again. We get lucky. We get an ideal solution. Now on this last one, this one gets really complicated. First off, the first two equations and first two congruences end up being identical. So we know for a fact right off the bat there won't be one solution, because what we have here then is, what was it, 8 equations? Oh, so 7 equations but 8 variables. So there's now more variables than equations, so we aren't going to get a single answer. There will definitely be variability to it. So we know that from the start this time, just by looking at it, but we do get lucky with this one. One of roughly in the middle, the formula for y5 is one term removed from just being the sum of all terms, so from being capital X, the complexity. So by adding to that, here we go. So we can just add the y6 to get the capital X, and what this then indicates is that if we want a minimal solution, we can consider the possibility where y5 is as small as it can be and x6 is as small as it can be, in order to get as small as possible x. Like, what if y5 could be the bare minimum of like 5, i.e. z5, and x6 could be 0? That would be the best case scenario if it is possible, I mean. And so that's what we consider moving forward as we go about seeing if that solution is possible. And it does work out nicely in our favor that it is possible. And then we have some variability again. There's the x4 plus x7, but that also ends up, you just need to look at it more closely and you realize, well, there is only one way to get our minimal solution, so we eliminate that variability as well with x, and that is to have the x4 and x7 be 0 and 0. I think, yeah, here I wrote it. And that is then how we got this solution. And so this solution is really mathematically complicated compared to the others to derive. And the complexity of the solution will show in the speedrun clip that follows. You're gonna watch this. This is interesting.
Now you might think, okay, maybe there's just a mistake in the math, right? Because it isn't used in the speedrun, so maybe even though it's less complicated than the solution used in the speedrun, maybe it just isn't actually a solution. Well, that's the thing. I tested it and I even uploaded it on YouTube. Take a look. So yeah, that's interesting. It's the solution used in speedrun is suboptimal, and this is likely because of how complicated this puzzle in particular is, and how complicated it is to derive a minimal solution. And now, like we see, it does work. And now, just to then I did check around on some guides for the game, and none of them used the solution either. And just to check that. And now, just to verify that it isn't the case that maybe there's something about the other solution that made it more optimal, I was, in fact, somebody noticed, I uploaded the clip that you just saw to YouTube, somebody noticed it. Saw Pawn, an active Nancy Drew speedrunner, they commented on my YouTube video of the solution, confirming that this is a new solution. They just genuinely didn't know about it. So, maybe you should try applying this method to some puzzles in an obscure 22-year-old game. You might just be the first person to discover a miraculously simple solution that has just been under everyone's noses. Hey, who says math isn't cool, huh? Isn't that cool? Don't you want to try that? Now, I do need to point out that this method is impractical to do by hand sometimes. On screen is an example of such a puzzle. This is from another Nancy Drew game. As you can see, this puzzle has 16 nodes, a whole 60% more nodes than the largest puzzle I've covered. So the resulting system is really complex. Thankfully though, such puzzles usually have inbuilt patterns to how the nodes interact with each other, which allows for other clever ways to solve them simply. Okay, so there's a surprise puzzle. Yay! Isn't that fun? Yo. Yeah, I didn't bring this up in the intro because I don't have a physical copy of this thing, so I couldn't really try it out, so I don't have a lot to say on it. But it's worth mentioning, because it's the only one here that isn't in a video game. It's like a physical puzzle. And so, yeah, this one that he mentioned is the Rubik's Clock. It's a handheld device. It is also of the type of puzzle we've been speaking of, but it's a special case where you have two types of nodes. Type 1 doesn't affect other nodes and can't affect itself, but it is affected by other nodes. It's affected by type 2 nodes. So type 2 nodes can't be affected by type 1 nodes. It can't be affected by type 2 nodes, but type 2 nodes can affect type 1 nodes. Yeah, and the type 1s are the clocks on the device, and type 2 is like different combinations of the pins being pushed up and down, and then the wheel you interact with, like the combination of pins and the wheel you choose to interact with itself, is that whole thing together is a node. And if you treat it like that, then it does satisfy the axioms of this model of this puzzle. It does apply, which is interesting then. So that was worth bringing up. Okay, time for the credits. Alright, so I want to mention, alright, I was introduced to the Rubik's Clock by a friend who knew of it somehow. They sent me a link. He sent me a link talking that where you could buy the product. and so that I then looked into that for the video. I of course have to mention Ersapon again, who the Nancy Drew speedrunner, who did verify that my solution to the senior difficulty puzzle was new. And then there was the gameplay of the the gameplay of the junior speedrun for the Nancy Drew game was by Yandamau211. Thank you to them. The gameplay of the senior speedrun of the Nancy Drew game was by the letter M. The Undertale Yellow speedrun was by Mario Man 47. The links for the speedruns and for Ashapon's channel will be in the description. The gameplay of the pyramid puzzle from Nancy Drew White Ruffle Bicycle Creek was by MNT Dumania. Their link is also in the description. And I, of course, have to thank the developers of these games. I enjoyed all 3 games shown in the video, especially Undertale Yellow, and it was Ghost Dogs of Moon Lake that inspired me to make the video. Also, the Nancy Drew games was something I grew up with, and they probably played some small role in my love for math and puzzles. Today, I mean, I even had a teddy bear growing up that I named after Nancy's teddy bear from the games, so that's interesting. But yeah, so all of the Nancy Drew games are available on Steam. Undertale Yellow is available for free, and not as in piracy. I mean, it's like by the developers uploaded on GameJolt. So the link for the Undertale Yellow GameJolt page will be in the description. But please don't play Undertale Yellow if you haven't played the original Undertale. Undertale Yellow is a fan game of the original and does contain some lore spoilers, even if most of the game isn't canon. I guess you could play Undertale Yellow first, just to see if you'd be willing to spend money on the original, because their gameplay is very similar. But yeah, that's the credits. Bye.